Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome today Jan SOIBELMAN from Kansas State University, and he will tell us about his work on Riemann-Hilbert correspondence from the point of view of holomorphic Floer theory. Jan, it's all yours. Take it away.
Thank you very much. In fact, it's a joint project or other program with Maxim Kontsevich, but I will tell you a little bit later. All right, so I start, with some very general remarks, kind of at a philosophical level, that people doing non-commutative geometry, but they don't know what it is. There is no universally accepted definition of what means non-commutative geometry or quantum geometry or quantization of some classical geometry. There are many examples, but in non-commutative geometry, the common thing is that you cannot use the notion of a point, so that's why it's non-commutative. So like assigning an algebra and non-commutative algebra even to a commutative space already makes it non-commutative. Or you can consider like modules of this algebra, or just define the category associated with topological space, or a manifold, symplectic manifold, and so on, and say that you quantize it. And there are, of course, many examples which you know well. There is, for example, in more recent, like brane quantizations of hyperkähler manifolds in physics, or, for example, older example, representation of theory of quantum groups, or more generally, quantized algebra. There are many of them. We will see some. Or kind of more sophisticated, you start with a real symplectic manifold, associate to it Fukaya category, and say that it's sort of a quantization, Floer type quantization. So there are many examples. And categorical approach to quantization, it has some useful consequences. For example, you can interpret various dualities in quantum physics or in quantum mathematics, whatever it means, as equivalences of categories. And for example, there are kind of Fourier-Mukai type equivalences, like Mukai equivalence of the derived categories of coherent sheaves on different abelian varieties. Well, geometric Langlands correspondence in algebraic geometry or representation theory, or a homological mirror symmetry. There is a typo in the word homological, sorry. And these are just few examples. So from this general perspective, my talk is devoted to two different quantizations of the notion of complex symplectic manifold. Everything is important, that it's symplectic and it's complex. Symplectic form will be holomorphic. And the main topic of my talk, generalized Riemann-Hilbert correspondence, abbreviated like this, it's a statement that these two different ways to quantize complex symplectic manifold are equivalent. So I start with a reminder of what is classical Riemann-Hilbert correspondence, sort of a historical history, very short history, because there are many works on that. So classical Riemann-Hilbert correspondence in dimension 1, which means it's on the curve, and even more basic, which goes back to Riemann and Hilbert, it's on CP1. It deals with, in their case, it's Fuchsian differential equations, so I will use kind of slightly different modern terminology. So I will start with regular singular differential equations, and this is an example. regular singular means that the right-hand side, in this case, it's just a scalar differential equation. A is a number, 1 by 1 matrix, if you'd like. It has a pole of order 1. So this means regular singular. And the only invariant of such an equation is its monodromy. So in this case, the fundamental system of solutions it's spanned by one function, and so this is a monodromy. Now, if you allow poles of higher order, like even in this one-dimensional example, allow pole of order 2, then monodromy is not the only invariant. For example, in this particular case, there is no monodromy at all. It's trivial because this is a solution. And so one should take into account the Stokes phenomenon and add Stokes matrices. So then the Hilbert 21st problem was a question of reconstructing the regular singular differential equations, more precisely Fuchsian, on CP1 from its sheaf of solutions, which is locally constant, and therefore equivalently from its monodromy. Because for the locally constant sheaf, the monodromy is the only invariant. So this is the Hilbert 21st problem, and as many of his problems, it's well posed, which means that it admits generalizations and ramifications, and I will discuss a brief history towards the main goal of my talk.
Sorry, may I have a question? Just a quick question. So you have one variable, so this one is a critical degree of the pole. In other words, when this equation starts to be irregular singular.
Irregular, it depends on the order of the pole. Starting from 2 and higher, it's irregular.
And how about greater number of variables?
That's what I'm heading to, you know.
Okay.
I told you that I'm telling you a short history. But
Okay.
first I start with a generalization of the regular singular case to higher dimensions. That was done by Deligne about 1970. And also he pointed out, and it's an important but almost trivial by now remark, that he reformulated the Riemann-Hilbert correspondence between equations and solutions as equivalence of two categories. Because, you know, originally at the time of Hilbert there were no categories, and so, well, you have a monodromy representation like CP1 with number of punctures, representation like local monodromies, representation of fundamental group of CP1 minus whatever n punctures, and you want to reconstruct a differential equation with poles of order 1 at these punctures, and which produces you the given monodromy. Now, the equivalence of categories, it's better, because now we have a category of vector bundles with flat connections. Flat is missing here, and which are regular singular on one side, and the category of locally constant sheaves on the complex manifold. In Deligne case, it was quasi-projective, but you can do in non-algebraic category as well. Now, then you should say what is what does it mean to have regular singularities? It's already non-trivial. you should consider certain compactification of X and require that this compactifying divisors poles of the matrix connection matrix is of order 1. And so then he proved this equivalence of categories. It's a volume of lecture notes. I forgot which one. And this explains this phenomenon that in the regular singular case, even in higher dimensions, monodromy representation defines you the equation, or if you like, the bundle with connection, up to a gauge equivalence. All right. Next, kind of a really big step of great importance, it's a work of Kashiwara at the beginning of 80s. It's a time when the theory of D-modules was born. In fact, it was born early in 70s, but main applications, kind of fundamental applications, it's the beginning of 80s. So instead of bundles with connections, which is the simplest possible example of a holonomic D-module, one consider more general holonomic D-modules, which means you like assign to X a sheaf of differential operators on X. X is a complex manifold, and then you look for certain type of sheaf of modules or this sheaf of differential operators. I can tell you what they are, but it's not really the subject of my talk. And so then on one side of the Riemann-Hilbert correspondence in the form which Kashiwara suggested was a category of holonomic D-modules with regular singularities. Again, one should define what it is. And on the other side, instead of locally constant sheaves, he considers sheaves which are locally constant only on a certain stratification of X. More precisely, he considers constructible sheaves. Even more important, that he realized that one should consider a derived version of the equivalence. It's not an equivalence of abelian categories or exact categories. It's really equivalence of the derived category, of the category of holonomic D-modules with regular singularities, and the derived category of constructible sheaves. The functor is very simple. If you have a D-module, you can take the sheaf of analytic functions, which is trivially a D-module, and like in algebraic geometry, you consider points of your sheaf with values in this OX, or more precisely R hom in the category of D-modules from M to OX. In plain terms, although the language becomes more and more advanced, you look not only for solutions for the kernel of your differential operator or collection of differential operators, but you look for co-kernels and even higher co-kernels. So it's indeed some X groups. All right, so then he proved the derived equivalence, and also he proved that under this equivalence, the abelian category of holonomic D-modules with regular singularities goes to some abelian category in the derived category of constructible sheaves, and in fact, it's a category of what is known as perverse sheaves on X. And so that's actually how perverse sheaves were born, independently, of course. Bernstein, Belenson, and then later with Deligne and Gabber, they worked out the full machinery of perverse sheaves. Now it's an industry, But that goes back to the attempt of people, in particular of Kashivara, to generalize Riemann-Hilbert correspondence. And basically, this is the end of the line for holonomic D-modules with regular singularities. Now, in the irregular case, there were later attempts, including actually Kashivara himself, to generalize Riemann-Hilbert correspondence by allowing irregular singularities, like analogs of poles of higher order. It's much, much more difficult. Even if you try to understand what's the analog of the Stokes phenomenon in higher dimensions, you will see that it's not easy, because the notion to have regular singularity essentially can be derived from the restriction of your D-module to any curve in your manifold. It's not the case for irregular singularities. In the case of the curves, which means meromorphic connections on curves, or bundles with irregular connections on curves, it was done by Deligne and Malgrange in the 80s. Malgrange wrote a book in French about that, but there is a very nice volume published by French Mathematical Society, which contains the correspondence between Deligne and Malgrange on that matter. And so when you read these letters, so you'll appreciate the role of Deligne in this. So his motivation was kind of a Hodge theory in the irregular case. In higher dimensional, it becomes indeed difficult, as I just told you, and the most advanced results were obtained by Daniola and Kashivara relatively recently. But again, the statement, whatever people are trying to do, it's like you look for the derived category of an appropriate category of irregular holonomic D-modules on a complex manifold and compare it with an appropriate derived category of constructible sheaves on X. So it's modeled after this Kashivara's work of 80s, from 80s. All right. Now, this is a part of the history, and as a transition to the subject of my talk, let me say that besides of differential equation, there are other type of equations which are sort of similar to differential, but they are not. For example, there are difference equations, or there are Q-difference equations, or elliptic difference equations. So they are not local, but they do exist, and people try to treat them to some extent analogously to differential equations. And in particular, they ask what should be the Riemann-Hilbert correspondence, I don't know, for Q-difference equations, for example. And there are works on that. They were proposed by different groups of people, which even did not know about each other. The statements look differently for different classes of equations. So then one
can just a basic question. So in this context of difference equation, what does it mean to be singular?
You see, I am giving a talk, so you'll understand later how to formulate all that in the proper way.
Okay.
Right? I do not want to review all the previous works. You know,
okay.
But I propose together with Maxim some general framework, and you'll see what it is. All right. So then the question, one possible way to motivate my talk is to formulate a universal Riemann-Hilbert correspondence, is generalized Riemann-Hilbert correspondence, which contains, covers all those known cases like differential, difference, Q-difference, but we should not invent, like you just asked, a separate definition of what is a monodromy, what is a regular singularity. So it should be sort of a universal framework. That's what we did with Maxim Kontsevich like more than 10 years ago. And it's a part of our big program. I cannot call it even the project because it's really a program, Holomorphic Floer theory. And our generalized Riemann-Hilbert correspondence, subject of my talk, it relates to different areas of mathematics. One is a deformation quantization of complex symplectic manifolds, and the Floer theory also in the framework of complex symplectic manifolds. Yeah, you see this full screen does not allow me to move easily from slide to slide. Now, I mentioned homological mirror symmetry at the very beginning of my talk as an example of duality. It's stated as an equivalence of two categories by Kontsevich at the beginning of 90s. And it might be useful for people who know something about homological mirror symmetry to compare with generalized Riemann-Hilbert correspondence, because somehow they're similar, although the relation of generalized Riemann-Hilbert to physics is not quite clear. If you make a comparison, homological mirror symmetry, which in physics, it's like in Calabi-Yau case, it's sort of a T-duality in the string theory. And mathematically, it has the A side, so you have a real symplectic manifold, and you take the Fukaya category of it. If you'd like, you quantize it in this way, assigning a category to a space, to a symplectic manifold. And homological mirror symmetry has a B side, which is a derived category of coherent sheaves on the complex manifold, another, which is very much different from the real symplectic manifold you started with, even if it was a complex. Well, and it's called mirror dual. A complex manifold. So homological mirror symmetries claim that A side is equivalent to B side. The Fukaya category of real symplectic manifold is equivalent to the derived category of coherent sheaves of the mirror dual complex manifold. Now, in generalized Riemann-Hilbert correspondence, which I will formulate later, we will also have a sort of analog of the A side and B side. And the framework will be complex symplectic manifold. Even the A side will be the complex symplectic manifold. The A side is called the Betty side for the reasons, for Hodge theoretical reasons. But you can think of it as an A side if you like. And we start with a complex symplectic manifold and assign to it Fukaya category. In fact, as we will see, a family of Fukaya categories, one parameter family. The analog of the B side will be called the de Rham side, and it will be not a derived category of coherent sheaves, like in homological mirror symmetry, but it will be its deformation in the non-commutative direction, in the direction of the Poisson bracket. So then we still have both sides of the future equivalence, but the RAM side is obviously different because it's a deformation of the derived category of coherent sheaves. But more important that there is no mirror dual. Everything happens on the same complex symplectic manifold. So, then it's for those who know something about homological mirror symmetry. All right. And now what I will do next, I will somehow describe, not with absolute precision, but somehow define the RAM and Betty side of the generalized Riemann-Hilbert correspondence, and then make a statement. So deformation quantization. So it's something which probably by now you know what it is, but I'll start with a toy model example, which is because I mentioned D modules, and in the simplest case, like of D modules, say on the complex line, D modules are modules of the Weil algebra. This algebra 1 stands for the dimension. You can do it in any dimension, of course. That's okay, but to connect the story with the deformation quantization, we need the quantization parameter, which is h bar. So instead of differential operators, we consider h differential operators. Yeah. The difference is minor, but essential, because now the algebra becomes a module over polynomials in h bar. So I can make a reduction at any point in the h bar complex line. In particular, there is a quasi-classical limit, which is a quotient of this quantum Weil algebra by the ideal h bar multiplied by this. So then it will give us a commutative algebra. It's a symplectic plane. Yeah. In general, here we are lucky because everything is a module over polynomials in h bar. In general, deformation quantization, in symplectic case, it goes back to many people, Flatow, Sternheimer, and, well, in fact, to physics of 20s, quantizing of the phase space. But the general theorem about quantization of Poisson manifolds is due to Kontsevich, and in any case, one should work over formal series in h bar and treat h bar as a formal parameter. Later, I will make some analyticity assumptions, but in general, this is purely formal. It has some advantages, because when you look for the h differential operator, you can look for new types of solutions, like a WKB solution. It's a solution of this sort, which is, in general, it's divergent. It's not a convergent in h bar, even if you fix x. All right. Now, more generally, the general setup, you start with a complex symplectic manifold. And I will assume that the algebra of analytic functions carries a star product. Well, this means, of course, the algebra of analytic functions can be extended, sort of. I tensor it with formal series in h bar, or more pedantically consider series of such type. The coefficients are analytic functions. And star product, there is a general definition of what star product is, but maybe it's better. For those who knows, they know. For those who doesn't, this is an example of the star product on the algebra of functions on the complex plane. If you take even two polynomials or two analytic functions, so it's a formal series in H bar, x and y are standard coordinates, and the fact is that this is an associative product. And in general, the star product makes this a priori commutative algebra ends with a non-commutative associative star product and makes it also a module or formal series in H bar. And again, in general, you can do it only locally, so you should cover your M by some Darboux charts if you'd like. Introduce a star product and try to glue it together. There are abstractions, but I assume that they vanish somehow. Anyway, you get a sheaf of algebras. That's my starting point. More generally, you have a sheaf of algebroids. All right, so then this is a quantized algebra of functions, analytic functions in my symplectic manifold. Modulo H bar, it is required to reproduce the original OM, endowed with a Poisson bracket coming from the symplectic form. So a DQ module, deformation quantization module, is a sheaf or whatever, finitely generated module. Let me skip the sheaf over this sheaf of algebras. It's an abelian category. Since we have H bar, so we should be a little bit more careful. We should kill the torsion. And so we should factorize this category by the subcategory of H torsion modules. So that's a category of DQ modules, which, if you'd like, it's an analog of the category of D modules in the case when M is an arbitrary complex symplectic manifold. And so, all right, so that's a remark that just for you that there are different versions of generalized Riemann-Hilbert correspondence, which we call global and local. I will speak about the global one. Local from global, just for your information, local means that I take a complex Lagrangian subvariety in M. In this M, I can take fix a complex Lagrangian subvariety and consider the kind of everything happened in its small neighborhood. Global means that all possible complex Lagrangian subvarieties will be allowed. Now, in any case, in order to formulate the statement, some additional choices should be made, and the reason is that this M is typically non-compact. For example, the story with H differential operators, it is related to the cotangent bundle. M is a cotangent bundle to a fixed symplectic, to a fixed complex manifold. And the cotangent bundle is non-compact. And this is important. For compact case, you do not have global functions, everything is sheafified. But even in non-compact case, you should choose a partial compactification. This is the main choice. There are some other which I will omit, but the most important, and the category will depend on the choice, it's a partial log compactification. Log means that it's a partial compactification of M by simple normal crossing divisor, and such that the order of the symplectic form, it has a poles on it, and the order must be equal to 1. For example, if you start with a cotangent bundle to a complex manifold, there is a standard symplectic form on the cotangent bundle. You can compactify the cotangent bundle fiber-wise. Replace every fiber, which is a vector space, by its projectivization. So this compactification is not log, because the order of the symplectic form is 2 at the compactifying divisor. All right, so then you should make such a choice, and in fact there is no canonical compactification, canonical log partial compactification. So having a fixed symplectic manifold, you can have many categories and many Riemann-Hilbert correspondences which depend on such choice. But when this choice is made, and later we will see examples, then we can define the analog of the category of holonomic D-modules. In this case, it's holonomic DQ modules. And roughly, you consider modules or this sheaf of algebras, and you see there is an H bar everywhere. And each module gives rise to a coherent sheaf on M, because it's finite type module. So it gives a coherent sheaf. And the requirement is that the support of this coherent sheaf is Lagrangian, can be singular Lagrangian subvariety. And moreover, since it can be non-compact, this Lagrangian is required to intersect this compactifying divisor in a nice way, something like transversal, to be transversal. Yeah. So then it gives an abelian category of holonomic DQ modules. And this what appears on the B side, if you'd like, on the drum side of the generalized Riemann-Hilbert. But in order even to state it, I will make some assumption which is quite strong, that this category, which is a priori linear over formal series, is defined in fact over a smaller subring of analytic germs at h bar equal to 0. For h bar differential operators for this quantum Weyl algebra, it's okay, and for some other example, it's also okay. But in general, of course, this is an assumption. All right, now Bethe side. On the Bethe side, it's very much kind of resembles of what's going on in homological mirror symmetry, but not quite. First, we look at the complex symplectic manifold as a real symplectic manifold. So then we will put it into the framework of usual Floer theory. So for that, we take the real part of the complex of the holomorphic symplectic form. But there are more which we will need and actually have to do in order even to state a conjecture. First, we need to consider the C-star action on my complex symplectic manifolds, and those are just rescaling of the holomorphic symplectic form. So h bar here, it's a complex number. Moreover, there is an imaginary part of the rescaled form, and we keep it also because in order to define the Fukaya category, we need a real symplectic manifold, but we also need and can and have to add so-called B field. And we take imaginary part of the holomorphic symplectic form and treat it as a B field. So with this data, one can kind of open whatever textbook or paper on Fukaya categories and try to assign a Fukaya category for each H bar, so there will be a family of them, to each of these real symplectic manifolds endowed with a B field. But in fact, since M is non-compact in this Fukaya categories business, there are some difficulties. One also needs to choose a sort of partial compactifications or, as they say, to control the behavior of Lagrangian, in this case, real Lagrangian, submanifolds at infinity. And so the compactification which we choose here, it's the same compactification as I choose here. So there is a special term of what we get. It's known as a partially wrapped Fukaya category, and I don't have time to discuss these definitions. So it's an A-infinity category, which means that there are higher composition maps. And maybe here this is only a slide where I say a few words about this category. Glob sets for global, because I consider all, say, real Lagrangians. And some of the objects of this category are real Lagrangian submanifolds of this real symplectic manifold, endowed with vector bundles together with connections, and these connections are non-flat in general. The curvature is a restriction of the B field to this real Lagrangian. In particular, if you take a complex Lagrangian submanifold, both real and imaginary part vanishes, so then you get a vector bundle on the complex symplectic on the complex Lagrangian submanifold endowed with a flat connection, so you have a local system. So some of the objects, but there are other. Also, the requirement, remember that on the drum side we required that supports behave nicely at near the compactifying divisor. One of the requirements on the Betti side is that the closure of these Lagrangians must be compact. And again, they should intersect transversally or something like that. I don't want to specify it. Now, here is a picture which illustrates the infinity structure for those who have never seen it. There are not only compositions maps, and from compositions map you like in the usual case, you have higher compositions, which mean that you assign something to a collection of Lagrangians endowed, for example, with bundles with connections. And this something, this infinity structure, is defined in terms of the moduli space of pseudo-holomorphic maps from the standard holomorphic disk on the plane with marked points at infinity. So you choose an auxiliary almost complex structure on this symplectic manifold, which has nothing to do with the original complex structure. You consider maps which are holomorphic with respect to this, or almost holomorphic, pseudo-holomorphic, with respect to this auxiliary almost complex structure, and you count them. The condition is that points go to the intersection of Lagrangians, arcs goes to Lagrangians, and in this case there is a well-defined moduli space, so you count them, and using this count, you define some linear maps. The analog of this story is Morse theory, when you define the Morse differential using counting gradient lines, and so that's an analog of that, Floer analog of that story. But the byproduct of this counting is that you count each pseudo-holomorphic disk with the weight, and the weight is exponent of the area of the symplectic area divided by h bar. So then the resulting category will be linear, or the so-called Novikov ring, which is written here. You see, these factors are exponentially small, if you like. If the symplectic area is positive, these are exponentially small, small factors. All right. So, but then in order to be able to compare the drum side, where I had a priori formal series in H bar, with the Betti side, where I have exponentially small series in H bar, I will make an assumption. I already made one on the drum side, analyticity assumption. And here on the Betti side, I also assume that in fact my category, global category, this family can be thought of as a single category of this Novikov ring, that is in fact defined, or the subring of, if you'd like, it's inductive limit, technically speaking, of the rings of analytic functions on small punctured disks. So which means that I consider germs of analytic functions on the disk which might have essential singularities at the origin, yeah, and I consider inductive limit over all possible disks, so it's a germs at zero, if you like, of these rings. And it's clear why I want analytic functions on the punctured disks, because these things can have essential singularities. All right, so then I have this ring. Of course, it contains inside the subring of germs of analytic functions on the small disk without any punctures, and therefore I can change scalars on the Dirac side to this bigger ring. All right, and then when this foundational work is done, which is quite complicated, technical, then the global generalized Riemann-Hilbert correspondence, which in general, in this generality, is conjectural, it says that if we change scalar to this ring germs of analytic functions on the punctured disk, if we change them in the category of holonomic DQ modules, so then both categories becomes linear over this ring, then there is a derived equivalence of the category of holonomic global DQ modules associated with an arbitrary complex symplectic manifold and its partial log compactification, and the Fukaya category, which is defined for the same geometric data. And another part which corresponds, if you'd like, to the Kashiwara statement about the abelian category of holonomic DQ modules. And the claim is that this abelian subcategory goes to the subcategory on the Fukaya, on the Betti side, which correspond to objects which are supported on complex Lagrangian analytic subsets. So in general, supports of objects here, if you can speak about supports, they are real Lagrangian. But those which are supported in complex Lagrangian, they correspond here to objects in the heart of certain T structure. So then the statement analogous to homological mirror symmetry, if you'd like, that the RAM side and the Betti side of the generalized Riemann-Hilbert correspondence are equivalent. So that's a general conjectural statement. And there was a question, where are singularities, how to think about monodromy and other things which people get used to in the theory of D modules. And they're all hidden in this partial log compactification. And the next will be a few examples, all in dimension 1. Where you will see how it works. All right. So let's start with differential equations, with, if you like, with Deligne-Malgrange Riemann-Hilbert correspondence. So differential equations, so if you like, meromorphic connections on a marked smooth complex curve. Marked means there are finitely many points where the connection has singularities. But control like meromorphic singularities. And so first we asked for the formal type. So instead of looking for indeed sort of in the complex category for meromorphic connections, we take their Laurent expansions at each of the marked points, and so we can speak about formal classification of the same data on the formal puncture disk, or better on its finite covering. And there is a theorem, classical theorem, could be found in some version in the textbook of Vazov, Fukuhara-Levell-Turitin, HLT theorem, which says that in the formal sense, any meromorphic connection splits, maybe after going to some finite cover of the puncture disk, to the direct sum of the tensor product. This is the connection with regular singularities, so it has poles of order 1 in the puncture. I is xi here, it's index of the puncture. So there are kind of finitely many of them, but this is the simplest possible irregular factor which correspond to the exponent of some, in general, Puiseux, but if you do not like rational exponents, you can think that it's a negative Laurent polynomial, so lambdas are negative, like exponent and minus 1 over z, like in my example on the very, very first slide, or whatever on the third slide. Yeah, so then you have a formal classification, if you like, sort of a Jordan classification for bundles with meromorphic connections. And let's call this a singular term or a regular term, which controls the irregular behavior and is responsible for the future Stokes phenomenon. And so every meromorphic connection gives at each singular point gives these irregular terms, and these pieces produces some monodromy. So we can reverse the logic. We can fix these irregular terms, yeah, And this gives us a category. Define the category with this notation. Conf stands for connections. It's bundles with meromorphic connections on the curve with punctures, such that formal types of each connection, of each object of this category at the marked points is fixed. It's exactly of this form with fixed, with prescribed singular terms. And so it follows from the original Deligne-Malgrange irregular Riemann-Hilbert that this category is equivalent to the category of what? Of locally constant shifts on the complement of the singular points. So that basically here we have just a monodromy as the only invariant. But in addition, for a small circle about each singular point, the fibers, we get a local system on this circle by restricting it from the complement to a small circle. And the additional piece of data is a certain explicitly described Stokes filtrations on the fibers. So then Deligne-Malgrange Riemann-Hilbert correspondence says that this category is equivalent to the category of locally constant shifts endowed with Stokes filtrations for each singular point. So the theorem says that this generalized Riemann-Hilbert correspondence is in fact equivalent to the original Riemann-Hilbert after some choices, which I will explain on the next slide. What are the choices? Remember that for Riemann-Hilbert we should have a complex symplectic manifold, yeah? And its partial log compactification. So X is my curve, so of course the only symplectic manifold is a symplectic surface, which is a cotangent bundle. But then I need to add to it the partial compactification to choose some log divisors such that I will get a Poisson manifold with an open complex symplectic leaf inside, and this compactifying divisor should encode all these singular behaviors at the marked points. And this is how it goes. There is a small theorem behind, but let's take any of these xi's. Let's x be a singular point, yeah? So then there is a collection of singular terms, negative Puiseux polynomials associated with it. Let's start with a fiber-wise compactification of the cotangent bundle, which means that we add at infinity a copy of the original curve. Yeah, it's the same thing. Yeah. So then this singular point has its cousin at infinity, let's call it P0. And then we start to make blow-ups of this fiber-wise compactification. We start to make blow-ups. First blow-up at this point, then we continue, so we have an infinite series of divisors. Collection of divisors, if we like, inductive system. Then the small theorem, which I mentioned, says that if we have a collection of singular terms from the very beginning, then there is a one-to-one correspondence. We can know which divisors correspond to these terms, which means that there is a one-to-one correspondence between the singular terms and certain finite collection of divisors, which are log divisors in this inductive system. So that's a kind of a non-trivial algebra geometric way to encode singularities. And so then we take this open symplectic leaf, cotangent bundle, which we had from very beginning, and we extend it by adding these log divisors. There are as many of them as singular terms. We should do it for each singular point. And so we can define the category of holonomic DQ modules, as I briefly explained. And we can define the subcategory in the Fukaya category in the partially wrapped Fukaya category of the cotangent bundle, generated by certain conic Lagrangians which hit only these new divisors. So that's an illustrating picture for the blow-ups. And on the next slide, I explain you why this is indeed equivalent to Deligne-Malgrange. Maybe let me first, this looks a little bit dry, let me show you the picture and then we'll go back. So these are my marked points. And I have finitely many singular terms. Let's choose this point. Then we look for a small circle. You see, we consider the real analytic curve defined explicitly by this formula, which depends on singular terms. Each singular term produces one closed curve. And I have as many of them as there are singular terms. And I do it for each singular point. Then I take a conormal bundle to each of these closed analytic curves. It's a real conic Lagrangian in the cotangent bundle. All right. And I take the union of all of these. And these are those Lagrangians which I mentioned here. Yeah. In fact, I should choose only 1/2 of them positive conormals, but let's forget about this minor thing. Now, the bridge from Fukaya categories to something which Deligne and Malgrange knew in the 80s is the description of the Fukaya category in terms of perverse or constructible sheaves. And the thing is that this Fukaya category is equivalent to what is written here in the bracket. It's constructible sheaf on the complement of my curve, considered as a real two-dimensional surface, with the union of finitely many points. I choose some small disks and I throw them away. This is one thing. I consider such constructible sheaves which have micro support or singular support in the sense of Kashiwara and Shapira, which belongs to the zero section and the union of these positive conormals which I depicted here. So then basically the Fukaya category is equivalent to the category of constructible sheaves on the base with a prescribed singular support. And this can be deduced. It's not a very difficult result, but it's easier to give a reference. It can be deduced from the more general and higher dimension work of Nadler, Schonde, Treumann, Zaslow. It's kind of old. By now it's old papers. All right. So then we are able to restate the conventional Riemann-Hilbert of Deligne and Malgrange as a generalized Riemann-Hilbert. And now let's consider another class of examples which are not differential. They are Q-difference equations. Let me skip difference. I don't want, because everything is here. whereas here we have a Q, which is, well, it's a fixed number, say, with absolute value from 0 to 1, this interval. And this is a Q difference equation. This can be, I don't know, meromorphic or rational function on C star. We are in dimension 1 again. This is an example of a holonomic QD module, which is a module of the quantum torus. And here Q is a number. If you want to think of it in terms of deformation quantization, you put Q equal exponent of h bar and treat h bar as a formal parameter. So it's a quantization of a symplectic torus of C star square, endowed with a standard symplectic form. But it is analytic. Remember, I made analyticity assumptions. In the case of D modules, I do have this analyticity because everything, like in the case of Weil algebras, is defined over polynomials in H bar. Here I also have analyticity. Everything is analytic with respect to Q. All right. So then Q is a number, so now, Q Riemann-Hilbert correspondence. It's Riemann-Hilbert for this type of equations. It's known since 2009 by Ramis, Salois, Zhang. There is a paper in archive. Well, of course, they formulated it in the way which is not suitable for our purposes. And in order to compare with generalized Riemann-Hilbert, we need to reformulate it. So how it can be done? For that, I need the notion of the anti-Harder-Narasimhan filtration. There is a notion of Harder-Narasimhan filtration, which everybody knows, like you have, I don't know, like coherent sheaf on a curve, which end out with a finite filtration, such that the quotients are semi-stable. In my case, the curve will be elliptic curve. But then in the Harder-Narasimhan filtration, the slopes of semi-stable quotients decrease. And this condition makes a Harder-Narasimhan filtration unique. Anti-Harder-Narasimhan imposes a condition that the slopes increase, and AHN filtration is not unique. Interestingly enough, so I didn't know that, but recently Graham Wilkin pointed out that anti-Harder-Narasimhan filtrations appear in differential geometry in the study of gradient trajectory of Young-Mills, of the Young-Mills functional, but of course we didn't knew that. We invented it for our purposes. And so there is a notion of the anti-Harder-Narasimhan filtration, and now I will use it in order to formulate the Riemann-Hilbert correspondence so that it will fit our framework. So we start with a symplectic manifold, which is a two-dimensional torus, and this is a standard symplectic form. Now, in order to take care about possible irregular singularities, and you will have problems with formulating what is it in the original terms, but geometrically, without Q-difference equations, similarly to the case of D modules on the curve, you should choose a partial log compactification. And you see, we start with a collection of rational arrays, and they will play a role of singular terms in the D module case. And treat them as a fan of a toric surface. And so the toric surface, any toric surface, is a partial log compactification. The choice of a toric surface with intersections of toric divisors removed, some finitely many points removed, gives you the category. All right? It's a new category. And what's the difference between different choices of toric surfaces? It's a different irregular behavior of solutions of UQ difference equation. And now when this choice is made, so we fix finitely many rational arrays, if you like, singular terms, we choose a straight line, arbitrary straight line, which splits these arrays into two groups, above the line and before the line. And slopes of these arrays will be treated as slopes of the semi-stables for anti-Harder-Narasimhan filtrations. There will be two of them. So this is a theorem restated Ramis, Salois, and Zhang. So fix a finite collection of rational arrays and a straight line, which separate them into two subsets. Consider the category of coherent shifts on the elliptic curve. Q is the same as in my Q difference equation. And consider such of them which are endowed with two anti-Harder-Narasimhan filtrations with slopes of each corresponding to the rays above the line and below the line. Then, on one hand, this category is equivalent to the one which Ramis, Salois, and Zhang put in the Q Riemann-Hilbert correspondence in their paper. But this category is equivalent to the Fukaya category of the toric surface with the fan given by the whole collection of rays. Or rather, partially wrapped Fukaya category, but let me skip this. There is a conjectural generalization. This is a theorem, but there is a generalization of this result to Q difference equation in higher dimension, and people even didn't know how to formulate it. It's a new conjecture. Then anti-Harder-Narasimhan filtrations disappear, but instead of rational fans of rays, we have a fan of rational Lagrangian cones in R2n. It's a different story. It deserved probably a separate talk, so let me not to speak about it. And the final example is an example of elliptic Riemann-Hilbert, and there are choices here. There is a choice of elliptic difference equations. So similarly to the Q difference, the curve is not arbitrary. In the case of Q difference equations, the curve must accept the action of multiplication by Q, the C star action, and here it must accept shifts by an element of the elliptic curve. So I take this is an equation on the elliptic curve. Ax can have some singularities, whatever, and U is fixed, it's a shift. So again, we can, there are two possibilities actually. This particular class of equations associated with the elliptic curve, elliptic difference equations. For that, we choose a symplectic surface, which is a product of elliptic curve with C star, with this symplectic structure. And the partial log compactification is a natural one. We add to C star, we add 2 points, so it will be this compact surface. But there is another elliptic case, if you'd like. For that, we start with a symplectic surface, which is a complement of CP2 to the smooth cubic. And there is a holomorphic symplectic form on this surface which has a pole of order 1 on E, on this cubic. So this is certainly gives you elliptic difference equation, but this gives you something else. And this kind of, if you like, a toy model of producing a lot of representation theory of quantum algebras, because the quantization of this symplectic surface is related to, I mean, it's in fact, it's modules over Sklenin algebras. Elliptic. So then, on one hand, you have this Odesky-Feigen elliptic algebras, and people indeed studied intensively the representation theory, but for some strange reason, mostly in the finite dimensional setting. What we kind of this way of thinking, generalized Riemann-Hilbert, that we should study holonomic modules over Sklenin algebras. Well, and it's a representation theory of some quantum algebra. So here we have an algebra, we can study its representation. In the case of 3A, there is no algebra at all. There is a category. And there is a huge paper, I would say, a book by Eric Rines on elliptic difference equations and non-commutative geometry, which you can try to read. And it's more than 400 pages, I believe, last version. And there are some elliptic Riemann-Hilbert stated in his paper, actually, very nice one. And so probably one can prove, we haven't tried, but it looks plausible that we can prove that generalized Riemann-Hilbert is equivalent, in this case, 3A is equivalent to the one he stated. All right, so these are three one-dimensional examples which illustrate our approach. So what is left, it's the last slide, I believe, 27 of 27, other projects and maybe speculations. Now, there is a non-abelian Hodge theory due to Carlos Simpson and other people, Carlet, whatever, many people by now. And the wild case, I mean, originally it was for, at worst, for regular singular connections, but later Bolch generalized Bolch and who else? Hurtubis. Anyway, it's joint paper. Generalized to meromorphic connections. Non-abelian Hodge theory in dimension 1, of course, Bolch generalized it, but in Simpson it's any dimension. So we propose generalization of non-abelian Hodge theory, at least for in dimension 1, but now it's not necessarily related to d-modules on curves, because we allow q-difference equations, elliptic difference equations. And the key role in this Simpson story, at least originally, was played by harmonic bundles. All equivalences go through the category of harmonic bundles on the non-compact curves. But in our story, when you go beyond differential equations, new analogs of harmonic bundles appear, and in fact they are periodic monopoles. One periodic monopole for difference equations, two periodic for q-difference, three periodic for elliptic difference equations. So that's a part of a generalized non-abelian Hodge theory. Now, if you kind of think in terms of this twistor family, in our case, of categories, or CP1, which is part of non-abelian Hodge theory, and here it's generalized, so you have family of Fukaya categories and so on, so on. You can ask questions which typically appear in this framework. For example, this famous, by now famous P equal W conjecture, and you can formulate it in this generalized non-abelian Hodge theory framework as well, like taking periodic cyclic homology of the Fukaya categories. Now, representations of certain quantized algebras. I mentioned Sklenin algebras, but for example, there are rational Cherednik algebras which appear at least in physics so far, in physics papers in the framework what they call brane quantization. There is a paper by Gukov, Karateev, Dupay, anyway, many people, maybe 5 or 6 of them, which they model certain finite dimensional representations of rational Cherednik algebras in terms of what they call brane quantization, and its immediate corollary of our generalized Riemann-Hilbert in that framework. Now more on the speculative side, but maybe not much. You know, in all the examples, for example, in this one, you see we have a C star action along one of the fibers. Here we have a C star action along one of the fibers, because I do not want to take into account the second C star action. In the D module case, we always have a C star action along the cotangent. So typically, many interesting examples in generalized Riemann-Hilbert, they appear, our holomorphic symplectic manifolds carry C star action. And there is, you know, in this symplectic duality story by Ben Webster with many collaborators, Kautis, Kamnitzer, and so on, they model the category O of Bernstein-Gelfand in the framework of complex symplectic manifolds and with 2 C star actions. One is missing. And for that reason, we can do less and we can do more. We can work with more general categories which do not look as a category O, like categories of holonomic representations of certain algebras. And this C star action, it's an analog of, complex analog of the Liouville vector field in symplectic topology. It gives rise to a certain Lagrangian skeleton inside of the complex symplectic manifold, and you can try to describe both categories, de Rham and Betti, in terms of certain shifts on this skeleton. So that's another direction which makes a connection with the Coulomb branch business, or maybe with some physics outside of the Coulomb branch for 3D and equal for theories. Now, finally, I mentioned the local generalized Riemann-Hilbert, for which I fix Lagrangian, complex Lagrangian inside, for example, this complex Lagrangian skeleton. It's a possibility. It's an ongoing project with Maxim and myself. There are many interesting new features which people either did not know or knew only tangentially, like new type of WKB expansions for conventional differential equations depending on parameters. Or, for example, since you saw blow-ups in my story, so one can ask what's going on when we do these quantum blow-ups. You know, people try to think of it like Vandenberg thought about non-commutative blow-ups of surfaces long ago in very general terms. But if your non-commutative surface is a quantization of a Poisson one, there are some interesting details, like, for example, a quantum version of Orlov theorem about the semi-orthogonal decomposition of the category of perfect complexes on the blow-up of the quantized symplectic surface. And this is a part of an ongoing project, but probably I should stop here. This is it. And now you can ask questions. Thank you.
Okay, thank you very much. Let's thank Jan. Let me switch on my camera.
Stop share.
No, I mean, you can still wait because maybe somebody will ask you to show.
All right. The only thing is that okay. I somehow stuck. I cannot now I cannot escape from the full screen mode. All right, so.
Okay, so are there any questions? Adam, Tomek?
No,
Tomek, go ahead. Go ahead, Tomek, show yourself. And unmute.
I have a question about the role of this symplectic structure. Can these results generalized to the direction of Poisson varieties?
Yes, of course. Some of them, not all of them. It depends what. You can, for example, and that's what we also do, quantize the category of perfect complex. I mean, if you start with, let's take, you start with a Poisson manifold, all right? So then you have a category, I don't know, of vector bundles, perfect complexes, or coherent sheaves. And then, well, abelian or derived doesn't matter. Well, it does matter in the end, but kind of, you have a category. You can ask about its deformation theory, which is controlled by some L-infinity algebra, and it gives you some formal moduli space of deformations. So then, in a sense, whatever deformations in the direction of a Poisson bracket, it's already in it. But the question is how deep you can go. As for generalized Riemann-Hilbert, I don't know how to do it. You can ask, but for me it looks as extremely hard project. Because, you know, if you go to the very, very beginning of my talk, there were words holomorphic Floer theory, yeah? Holomorphic means that it's for complex symplectic manifold, but essentially it's a Floer theory. Floer theory is for symplectic manifolds. You should have symplectic somewhere. So if you have Poisson, you can decompose it into symplectic leaves, which somehow interact when you close them. With each symplectic leaf, you can try to associate some kind of Fukaya category, but then they should interact somehow. It's a diagram of categories. It looks extremely difficult. I have no idea what can be the answer.
What could be the analog of Lagrangian submanifolds in this Poisson case?
No, there is no Lagrangian. Lagrangian is just to formulate Riemann-Hilbert, because even conventional Riemann-Hilbert, it's for holonomic demodules. For holonomic, singular support is a conic Lagrangian. So it's something finite. It's if you'd like, it's differential equation that depend on finitely many parameters, solutions. In general, you can speak about all the modules. That's okay, and then you can do in Poisson framework as well. Like you quantize, for example, your sheaf of analytic functions, which is a sheaf of Poisson algebras. You get some sheaf of quantum algebras if you are lucky, or algebroids if you are not that lucky. You can look for modules of finite type over this, but then it depends on your fantasy. You can stop here and not ask anything. That's analog of the category of all D modules. Or you can ask the supports of the coherent sheaves modulo H bar to behave nicely with respect to the stratification of your Poisson manifold by symplectic leaves and intersections of their closures, but I don't know even how to formulate it. It's even with, with our framework, we can prove, frankly speaking, very little, more conjectural. For general Poisson, yeah, I can produce several fantasies, but but I'm not responsible for what I will be saying. Yeah, so it's...
Okay, thank you.
Okay. Anybody else? Any further questions? Adam, are you happy now?
Yes, I'm happy.
Okay. Anybody else? No, I don't see any raised hands. So in this case, yeah.
Excuse me, I have a question.
You do? Oh, I stop sharing, but I can start to share again.
You should react a bit faster.
Share, maybe it will not be
I'm
full.
sorry for my...
No, that's fine, that's fine.
I think at page 14 of your slide, I think it was
the problem is that in the full screen, I don't know what is it. Okay, I will see it. Yeah, this is page 14.
Yes. You wrote that there is a vector bundle on every Lagrangian submanifold with a connection whose curvature is the imaginary part of this complex symplectic structure. My question is that is this vector bundle, can this vector bundle define globally on the complex manifold or no?
No, not at all. No. The answer is immediate. Of course not. It's not. It's very specific. It's each Lagrangian defines you, if you'd like, kind of a local category. You consider bundles on this particular Lagrangian with connections, and that's it. You cannot extend them, of course.
So the vector bundle depends on choosing the Lagrangian, yes?
Absolutely, you're absolutely right. And
can one introduce that bundle explicitly in terms of L or something?
No, it's not one. You consider all of them. For example, when you take a Lagrangian zero section in the cotangent bundle, all possible flat bundles on the base will be okay. You will get the whole category associated with a single Lagrangian, so you cannot describe them. It's a category.
Yes, I see.
Yeah.
Okay, thank you.
Okay, so let us thank Jan again for his very fascinating talk. Thank you so much.
You're welcome. Okay, so thank you for coming. And so then, goodbye.